good to start.
Okay. Is there anyone, Alex? Is there anyone on the offline?
Yeah, there's one person offline.
One person offline. Is it connected right now?
Mm-hmm.
Okay, perfect. Hey guys. Good morning. I'm just gonna go a little bit about my background, and then we can start there. So my name is Mahdi. I did my master's in manufacturing design at USC in 2012, and I did my Ph.D. in manufacturing, focused on 3D printing in 2012 as well. So I got a master's and a Ph.D. And then in 2013, I did my postdoctorate at USC, focusing on additive manufacturing and metal fabrication. And also I taught at USC the classes called manufacturing processes. And currently I'm a full-time faculty at California State University in Long Beach. I also collaborate with companies, Northrop Grumman, Boeing, and Aerospace Corporation. My projects are focused on mainly metal 3D printing, automation, and material development for both composite and metal matrix composite. So I will take care of this class for you guys. I will be focusing on material section. And so this lecture has two parts. The first part is gonna be focused on going through the PPI book. And I made some slides going into more depth, mainly bringing it from this book, Manufacturing, Engineering, and Technology, which is a very good book. I will leave it here for your reference if you want to take a look at it. The PPI book, the problem I see is that it doesn't go into depth in some parts that is very common to see in the FE test. So what I did, based on the trend that I see some specific problems that are repeated every year. So I'm gonna go into more depth on those common problems. And then we do an overall scanning of the other topics as well, just to have a broad understanding as well. The time is limited. We have 3 hours, so we cannot cover everything. So I'm going to focus on the main problems and practice video on the main problems that you're going to see in the test. Any questions from me? You guys all good? So with that being said, I'm going to go through the some diagnostic exam test problem, just to let you know that what kind of problems we are going to see and we are exposed to. Then we're going to start the actual lecture material. So question number 1. I see it. So the results of a tensile test on a round specimen of a given material are shown. So we have the stress, engineering stress. We have the engineering strain. This is the specimen. The diameter is 1.308 centimeter, and it follows this path. The initial portion, which focuses on the elastic range, has been elongated, and is asking what is the nearly the yield stress. So in these problems, what is very common is that you have to understand that when it's elastic, when it changes to plastic, and also you have to also focus to see what are the if you have some unreasonable behavior, how we can take care of that. So at the end of this lecture, when we come back, we will see how we can take care of this problem. So I'm just going to go scan the problem, give you an understanding what kind of problems you might see. Then we're going to go solve it at the end of the lecture when we understand everything during the class time. The second was the activation energy for creep is 161 kilojoule per mole for a given alloy. If the applied stress is fixed and the stress sensitivity remains the same, by approximately what factor does the creep rate change when they have a temperature rate change? So then you have to see what is the activation energy for creep, and you need that formula from your formulas handbook, and from there you go ahead and find the change in ratio. We're going to go through that as well. Question number 3, there's a phase diagram given binary phase diagram. What is the most nearly the percentage of liquid remaining at 600, so this is like a 600 temperature, that results from an equilibrium cooling of an alloy that contains 5% silicon. So you have 5% here, so you're at this specific point, and the question is asking you what is the percentage of liquid, what is the percentage of solid. So there are two kind of problems that you might see in the FE test. One of them is the mix that you have. I will see if I can draw it here for you. Let me see if I can get the pen. Here. So if I click this, I can write here. Oh, perfect. So when you're at this point, you have a mix of solid particles. So in the FE exam, what they sometimes ask is what is the percentage of these solid particles? And this is liquid. So you have liquid, and then you have solid. So one question is what is the percentage of the solid and the liquid? The other question is what are the percentages of the elements inside the solid, and what are the percentages of the elements inside the liquid? So for this solid particle, what is the percentage of the silicon inside the solid, and what is the percentage of the silicon inside the liquid? So there are two different questions that you will be exposed to. You have to tackle the problem accordingly. So we're going to go through that as well. The other one is the stress strain diagram, which we're going to cover. Then you have some statements about strain hardening, work hardening, heat treatment that we will cover in class. Then you have a different stress strain diagram that correlates to ductile material and brittle material. So you also have to have quite an in-depth understanding of the ductile material and brittle material and how they behave by alloying. Then you have statements in regards to different type of steels, additives to a steel, and different type of materials, which you're going to cover in class in my lecture. Then binary phase diagram for steel is very common to be given in this type of exam. So we're also going to cover binary phase diagram for steel, cementite, perlite, ferrite, austenite, and so on. And the rest of the problems follow the same manner, different metals, different alloys, and so on. So you just have now you have a understanding what kind of questions you're going to see, and I will go ahead and solve these problems for you once we come back. So now let's go ahead and start the actual lecture. So the first part of the lecture is about materials and material selections. I'm going to go through the PPI book, do a quick scanning, then I'm going to go through my lecture, give you a more in-depth review. So materials we have ceramics. Ceramics consists of glass ceramics, glasses, bricks, graphite. So any metal oxide forms a ceramic, like zirconium oxide, magnesium oxide, and so on. Then you have composite. Composites are two different materials put together. For example, you have prepegs in polymer composite. You have a base fabric, a prepeg reinforced by resin. So you have two different materials. You also can have ceramics in metallic part. For example, you have two kind of metal phase mixed together. For example, you have cementite, which is very brittle, mixed in ferrite to create a composite. So there are like a different type of like composite materials that you can we will study. Then you have different kind of metals, ferrous metals, for example, carbon alloy, stainless steel, and tool steel, and so on. Non-ferrous metal, for example, any kind of like a non-metallic base, aluminum, magnesium, copper, nickel, and so on. Then you have plastic, thermoplastics, thermosets, and elastomers. So the book goes through very brief of these discussions. So what I did, so this lecture is going to be larger than 3 hours, which the institution is trying for me to go through this. So I'm going to go and into more depth of each of these materials and talk about crystal structure and so on. And then we're going to come back and discuss further. So I'm going to do a very quick scanning of my lectures that I go through my material selection and manufacturing process, which I made my lecture aligned with what you see in the FE test. So you press F5, slideshow, okay. So I'm going to go talk about metals, the structure of metals is the base of the, which is more common to see in the FE test. I'm going to talk about the crystal structure. I'm going to talk about the effect of grain and grain boundaries that you will see as well. I'm going to scan, since your time is not limited, I'm going to scan the non-important parts. So metals, if you look in the periodic table, you have alkali metal, then you have like alkaline metal, then you have transitional metal, then you have a basic metal, then you have semi-metal, like semiconductors, then you have non-metal, then you have noble gas. Overall speaking, if you, when you look at the periodic table in your handbook, if you look, metallic parts are more fall towards the left side and non-metallic parts towards the right side. Also in the periodic table, when you look in the FE test, most metals that are more shifted towards the left-hand side are more like they have a lower mechanical property, they have a lower density. As you move towards the right side, they have a stronger mechanical property. They also have a higher density, overall speaking. Just to give you a synopsis, for example, in alkaline metal, the first kind of metal, for example, one example is sodium. Sodium is very light. It stays on top of the water, and sodium also has a melting point 97.7, which is lower than the melting point of water. I'm just going to scan this very fast. Overall speaking, in metals, it has a low ionization energy. It has positive oxidation states. It's very hard. It has a high melting point. It has high electrical conductivity. Is malleable. And transitional metal have a mainly follow filling up the d orbit. Metals have ionic bond. By ionic bond, it means that metals have positive state and you have electrons wandering around, which, I'm sorry, non-metallic metal has a metallic bond, which have like a positive charge and electrons falling around. Because of that, it is a high thermal conductivity, high electric conductivity. Metal commons property, they're shiny, they're solid at room temperature, high melting point, high density, low ionization energy, usually has a high deformation, is malleable, they are good thermal conductors, they are good electrical conductors. Metals have a crystal structure. There are like a total 11 crystal structure for metallic parts. BCC, FCC, and HCP are common crystal structures. So BCC, body cubic center metallic parts, just to let you know, some examples are lithium, sodium, potassium, chromium, barium, tungsten. These are metals that are very brittle. So metals that have BCC crystal structure, body cubic center, are very brittle. Then you have FCC crystal structure, face cubic center. In face cubic center, every unit has 1/8 of an atom at a corner and half an atom at the surface of the cube. Some of the metals of FCC are copper, aluminum, gold, lead, nickel, platinum, and silver. Metals that have a FCC crystal structures are more malleable and are easy to deform. Then you have hexagonal closed packed HCP crystal structure is very common for for elemental metals such as beryllium, cadmium, magnesium, titanium, zinc, and zirconium. Again, metals that have a HCP crystal structure, they are very brittle. We have two types of deformation, elastic versus plastic deformation.